This video will cover the second part of the fundamental theorem of calculus. In fact, this is actually the first part. The other day we looked at part 2. That was to find an integral, take the antiderivative and plug in the upper limit, and then plug in the lower limit, subtract the lower limit from the upper limit. It's actually an easier one to prove. This part of the theorem we're going to look at just through some examples. So we have two goals for the day. We're going to try to create a function that is based on an integral and then take the derivative of that. And if we can find a pattern, we're going to actually understand the second part to this important theorem. And if we can do that, then because we can talk about integrals as functions and we still take derivatives, all the things that we learned about what it means to be increasing, decreasing, concave up, concave down, etc., we can use to answer a variety of questions. So in our first example, we're going to be looking at a function that is, it says it's odd, so it's going to keep kind of going like this over this way, and it's periodic, so the pattern is going to continue. And we also know that the area under the curve from 0 to 1 is 4/3. We're going to define the function capital F that we're interested in as the integral of this function from 0 to whatever x value we're looking at. So if we were to think of our table here, I might start with some of the easier ones here. If I start with 0, if I plug a 0 in, the area under the curve from 0 to 0 is 0. And then the area under the curve from 0 to 1, the book tells us, or the problem tells us, is 4/3. The area under the curve from 0 to 2, so this much right here, well, they're going to kind of undo each other, so that's going to be a 0. And then if we were to continue until 3, that would also be 4/3. So then it's kind of interesting to go back to the x value of -1. So this area right here is 4/3. Actually, we count it as -4/3, but because the limits are backwards, this answer right here would actually be 4/3 because we went from 0 to -1. We want to count that overall answer. We want to flip the sign. Okay, so we are able to plug in different x values into this idea here, and it spits out y values. It spits out outputs, and so that would define a function. Next example, same sort of thing. We have this graph. This is going to be graph w of t, and we're going to define function g of x as the integral of w of t, starting at -2, going all the way to whatever x value we choose. So again, if we were to plug a 0 in, so what's the area under the curve from -2 all the way to 0? Well, this little triangle and this little triangle undo each other, so we just get 0 from -2 all the way to +2, so we need to think about all of that area. Again, these two pieces would just undo each other, so it's a matter of finding this area right here, this little house shape, and we'd have 1, 2, and then these two triangles together would get us 3. And then from -2 to -3, right? X is going to be -3, so we're going to start here, go that way. The overall area is -1.5, but again, because the limits were backwards, we have to flip the symbol, so we get +1.5. So we are able to define a function as an integral. It gives us outputs, so that's fantastic. Now we want to know, that was kind of goal 1 if you look at the top of the notes. Now we want to figure out what happens when we take the derivative of these things. So in example 3, if we say that g of x is the integral from 0 to x of cosine of t, we want to find g prime. We're just going to go through a bunch of examples like this. We want to evaluate the right side of that equation. So what does this mean? Okay, that's what I mean by the right side. So we need to take the antiderivative. The antiderivative of cosine is sine, and we'd have to have sine of x minus sine of 0, which is really just sine of x minus 0. So the minus 0 kind of doesn't matter, but I'm just going to leave it there anyways. Now if we were to take the derivative in part B of this answer that we got here, derivative of sine of x is cosine of x, and the derivative of 0 is 0, so it doesn't matter. And so here is our overall answer. In example 4, same basic idea, but we now have a different lower limit. So again, I want to evaluate the right side of that equation. I want to evaluate what this thing is. So again, the antiderivative of cosine is sine. I'd have a sine of x minus sine of a negative 2, which is not very easy to undo, the sine of negative 2. Just kind of have to leave it like that. But then we go to part C and we take the derivative. Well, the derivative of sine is cosine. And then sine of negative 2 is just a number, so it's going to be the derivative of a number is 0. So again, nothing that I need to write for that second part. And the big thing now in part D, did changing that lower limit from 0 to negative 2 matter? No, it did not. So hopefully we're starting to see a pattern when we have it phrased like something up here. We can basically just take that x and put it in place of the t, and that's going to be our answer right there if we were saying what is the derivative of this function. So just to clarify that idea a little bit more, let's suppose that g of x is cosine of t, the integral of cosine of t from a to x. A can be any constant right away. What's g prime of x going to be? No matter what a is, we can, let's get my pen here. Right away it's going to be cosine of x would be the derivative of that idea. Again, just look for the important function right there, and instead of that t variable, you would just replace it with an x. And then in example 6, the only difference from the example 5 is that the limits have been flipped around. And so when that happens, we have to flip the sign of our overall answer. And so we would get negative cosine of x for that. So in example 7, why is this one more complicated? If you look at the overall equation, there's more stuff in the function. In fact, we might just say it's more complicated. There's more ideas going on here. There's a function within a function, you could say. But again, we want to do the same thing. We want to take the derivative of what we're expressing as g of x. So this thing right here. So let's say that the antiderivative for this one, because it's more complicated, if we were to go through and do this as we did the previous ones, we would want to find the antiderivative of that function that's there. Well, that's kind of complicated. Let's just pretend that it's h of t. That's our antiderivative. That means that h prime of t is simply, come on, Ben, this same equation, right? If the antiderivative of this is h of t, that means h prime of t is just what we started with. We're just going one step up and then going back one step down again. So using h of t, let's kind of do the same thing to evaluate the right side of the equation. I would want to take the antiderivative of that, which we said was function h, and I would plug in an x, and then plug in a 1 and subtract them. And then in part D, I want to take the derivative. So what we're doing again is we're doing the integral, and then we're taking the derivative. And when I take the derivative of h of x, I get h prime of x minus, and then h of 1 is just going to be, that's going to be something I would get a number for, right? If I plug a number into an equation, I'm going to get a number. So derivative of a number is 0. And then if I simplify this, h prime of x, remember, is just what I started with, except up here it had t's. So here it's going to be 1 plus x cubed. And then minus a 0 if we really wanted to, but I'm not so worried about that. So again, it still works, that same thing we had with the cosine integral from examples, I think it was 3, 4, 5, and 6. It still works here, even with a more complicated function. We're still able to phrase it that way. So that's basically the fundamental theorem of calculus, or at least this part of it. If I want to take the derivative of an integral idea, and the lower limit is a constant, the upper limit is just x, when I go through this whole process, I will always be able to say it is just, come on, pen. Okay, it is just that function f, but I replace that original variable, in this case a t, with an x, because the process of taking antiderivatives and then taking a derivative, it will always work out that way. Now this can certainly get more complicated. But that's kind of the main basic idea, and hopefully just by running through a few examples of that with you in this video, that will help. So let's look at just a couple more examples here before we wrap up this video. The big issue here, same sort of question. Obviously the function looks kind of complicated, but the limit up here should look a little bit more complicated too. 3x squared, it's not just an x. So what's going to happen for something like this? Again, let's say that the antiderivative of this main function is h. So antiderivative is h. The process that we go through and do this, I'll switch colors a second, is we still want to take the antiderivative of that idea, and so we already said the antiderivative is going to be h. So in this case, I would write that as h of the upper limit, so 3x squared, minus h of 2. So that was kind of like the part A or something like that for the first couple examples. And then I would want to take the derivative of this idea. So part B would be something like take the derivative of this. So what's the derivative of h? It's going to be that equation that I have in the red box up there. So I would have a 5, but instead of t being squared, I'm going to have a 3x squared being squared, minus a 6, 3x squared, plus a 1. But then if I think about this, I have 3x squared inside function h, and whenever we had to take a derivative of something like that, we had to use the chain rule. So there's going to be the derivative of 3x squared, which is 6x after that. And then we still have to take the derivative of h of 2. Well, the only difference there is I can plug a 2 into whatever this antiderivative is. This would spit out a number. So we're taking the derivative of a number, it's 0. In the end, this idea right here is my answer. That's going to be the derivative of this thing. So the general rule still applies. I can still take this idea and replace it with the upper limit, but because the upper limit was a little bit more complicated, I just need to remember to use the chain rule at the end. And I could certainly simplify this as well, but we'll just leave it there for now. And then one more tough example here. Now notice that both of the limits are changing. There is no constant. But we could still go through and do the same thing. We could still say that h is the antiderivative. And so in part A, they might ask us to take this right side and somehow evaluate it. So we would find the antiderivative of that function, which we're calling h. And first I would plug a 3x squared in. And then I would plug a 5x in. But then we want to find g prime, right? This is how we might represent function g. We want to find g prime, so I need to take the derivative of this. And so the derivative of h, because h is the antiderivative of this, the derivative of h is this idea right here. So I would have, grab the pen again here, I'd have square root of 1 plus, and then where there's a t, I'm going to put the upper limit. So I'd have a 3x squared. That would have to be cubed. And then because that was 3x squared inside function h, we need to use the chain rule. So I'd have a times a 6x at the end. And now this one, the second part does matter, because now I'm not just plugging in a number into function h, it's an equation. So I'm not going to get just a number answer, I'm going to get something that still involves x. So now I would need to do this again. So I'd have a square root of 1 plus, and then in parentheses I'd have a 5x, that replaces the t, still has to be cubed, and then again the chain rule, so times a 5 at the end. And we could simplify this probably a little bit more, but for now we'll just leave that as our answer. But these two examples hopefully show you the following. Okay, that even if these upper and lower limits do have functions involving x, you just have to use the chain rule. This does look quite complicated. If you kind of break it down into the individual pieces, it's not as bad. We can certainly talk about what that means in class, but yeah, it's a tough idea. It's not simple, but if you take the time to kind of understand what this notation is saying, you'll see in here. This is the first part. Come on, pen. Okay, that was the first part. Here's the chain rule. Here's that second function that was the one involving 5x, and then here's the chain rule multiplying by 5. So it's kind of built in there, but I would just remember the patterns that you saw through these examples. All right, we better stop there for now, so jot down any questions, and we'll see you in class.